Hello, welcome to Garch time series models. So here's an overview of what I'm going to be talking about today. The motivation behind Garch, the ARIMA model, which is we're going to compare the two, Arch, the foundation, for Garch 1.1, and 5 practical applications. So what's the motivation? Financial markets don't move in a constant smooth rhythm, they move in regimes. When a piece of significant news hits, a central bank interest rate hike, a geopolitical event, or a corporate earnings surprise, which are all random, the market doesn't process it instantly and move on. It enters a high energy state where participants are debating the new price. This leads to a cluster of large price movements. A more concise term for this phenomenon is called volatility clustering. Now, Garch is a model that recognizes this stickiness of risk. It acknowledges that the variance of returns is not an independent coin flip every day. Instead, variance is autocorrelated. If the market was turbulent yesterday, the probability of it being turbulent today is statistically higher than average. So let's do a review of the ARIMA model because it'll help us explain the Garch model. ARIMA models the conditional mean of a time series by combining past values, which are the autoregressive components, and the past forecast errors, which is the moving average component, to predict the future path of a variable. It essentially cleans the data of its predictable trends and patterns, leaving behind a set of residuals that represent the unpredictable shocks or noise in the market. By establishing this baseline, ARIMA provides the necessary raw material for Garch, which then takes those residuals and models their changing intensity, shifting the focus from predicting direction of the price to predicting the scale of the risk. Okay, risk and variance are interchangeable. So we've got this equation, yt, the value of the time series at time t, phi, the autoregressive coefficient measures of how fast past values influence the present, yt minus 1, lagged values, theta t, the coefficients that measure the impact of past shocks on the current value, the error term, today's error term, which is unaccounted for. So let's talk about the model specification in Python and the error term. So we've got our equation. We've got ARIMA PDQ. Now this is something that would be like a Python function, okay? P would be the autoregressive component. D would be the differencing, making it stationary. And we saw this in detail in an earlier video on ARIMA. And Q is the moving average component. Now the error term is normally distributed with 0 mean and sigma squared as the variance. The expected value of the error term is 0, and the variance of the error term is sigma squared. Now the error term is considered constant, and there's a term for that, which I'll be discussing shortly. So in an ARIMA model, homoskedasticity means the residuals have constant variance over time. So that's the term, homoskedastic. The shocks may be autocorrelated in levels, but their volatility does not systematically change or cluster. Now here's something that you see where there's a constant variance. Now you do see several outliers, but in general, all of this, the residuals are banded between 3 and -3. And you could see that 0 is the mean value. And we saw that in its equation form, right? In a Garch model, heteroskedasticity means the variance of the residuals change over time and depends on past squared shocks and past variances. Now we saw that in the ARIMA model. The shocks are scaled by theta, but they're not squared. Okay, so the differentiation between ARIMA and Garch, quickly, if you pick it up, or if you quickly see this, is that it's squared. The error term is squared versus it not. And then it also uses past variances, okay? Where the ARIMA model is just trying to model the mean level, right? The mean return. This is modeling the volatility of the return. So this produces volatility clustering, where periods of high volatility tend to be followed by high volatility and low by low. Now this is an example of heteroskedastic residuals where the error term is not constant. You can see that it's basically some type of megaphone type diagram, right? Where the large movements move in move together with large movements. Now let's talk about Arch modeling the variance. This is the foundation for understanding Garch. So Robert Engel noticed that in finance, even if you can't predict the direction of the stock ARIMA, you can predict the big moves following big moves. This is called conditional heteroskedasticity. Arch ignores the mean and focuses purely on the variance of the residuals left from your ARIMA model. Now we've got this equation here, and I'm going to explain it in detail. Now the left-hand term, the sigma squared t, is the conditional variance. This is the variable we're trying to solve for. It represents the predicted intensity of the market's movement for the next period. It's conditional because it changes based on the most recent available information, right? And that could be denoted by that summation symbol with the lags, right? I equals 1 is the most recent period. The constant omega, this is the baseline or floor of the model. It represents the inherent long-term average level of risk that exists even when there is absolutely no news or market drama. Okay, so say if there was no such surprises, there was nothing, sigma squared t would just simply equal to omega. Okay, so that is something that would occur if there's no random events, no news, no nothing. Okay. Squared innovations, the shocks, these are the actual surprises that just happened in the market. We square them to focus purely on the magnitude of the move rather than the direction. A massive crash or massive rally both count as high intensity shocks that increase the variance of the next step. Okay. So you can see the difference between that and ARIMA already, where we square that to the error term, whereas in ARIMA, it was just regular, right? We just had the error term, and it was scaled by theta. And in our case now, in the Arch, we're scaling that error term, squared error term, by alpha. So alpha is the volume knob, right? It's for the shock. It determines how much the current variance reacts to a recent surprise, okay? So it could be amplified or dampened based on the news event, okay? If it's low, it's going to be more slow and it's going to ignore the spikes, right? If it's high, then it'll amplify it, the spikes. And then finally, the order Q. And this is simply measures the memory span of the model. It's the number of prior days the model looks back at to see how many shocks it needs to factor in today's risk calculation. Okay. So it's looking just purely at the shocks. So here's a graph of the returns of a simulated arch. And on the bottom is the volatility. In both graphs, you're going to see huge spikes, whether upward or downward. I see a couple between 600 and 800. But those quickly revert back to a baseline level, right? There's no memory. It's not capturing any memory. In order to do that, we're going to have to use Garch 1.1, right? If we want to capture the memory. So this model will capture these huge random events, but it'll quickly revert to some baseline level, which is omega, okay? Now let's see how Garch 1.1 actually improves upon the arch model. So Garch improves by adding that memory component beta, and that includes the previous period's predicted variance, allowing the model to capture long-term volatility clustering with far fewer parameters. While Arch only reacts to immediate external shocks, the news, Garch accounts for the persistent state of the market, effectively acting as an infinite lag Arch model. This makes Garch more parsimonious and better at representing the regimes of high and low risk seen in real-world financial data. So sigma squared is equal to omega plus alpha, the squared shock residual, plus beta sigma squared t minus 1. Now we add that term beta sigma squared t minus 1. The squared residual lag sigma error term squared t minus 1 represents the magnitude of yesterday's unexpected market shock, which we discussed. And it's stripped of its direction so that both large gains and large losses are treated as increases in volatility, as we discussed. By squaring this prior error, the model creates a direct mathematical link between past intensity and current risk, allowing the variance to recently react dynamically to recent bursts of activity. Now, I do want to discuss that error term a little bit more deeply. It's decomposed into sigma t and zt. Now, zt is a standard normal, okay? The sigma, this is the conditional standard deviation to scale. Z, this is the standard normal random variable, the surprise, okay? So I do want to make the point that, this is a random, it's driven by random variables, the surprise. The coefficient that scales the lag surprise, if sigma is high, then the model is jumpy. One big move yesterday causes a massive spike in the risk forecast for today. Okay, so the alpha is what's basically turning it up or down, just like the arch. I do want to make an important point though. The ZT could be replaced by something like a T distribution if you believe that market events are going to be fat-tailed, okay, where improbable events have a higher likelihood of happening, you're going to want to use something like the T instead of the standard normal. So finally, what makes a difference between Garch and Arch? It's the beta. That's what makes it different. And it scales yesterday's predicted variance, acting as the memory that keeps the volatility state consistent over time. So here we have that conditional heteroskedasticity for Arch. You can see the big spikes I mentioned earlier, how quickly it reverts back to some type of baseline level, okay? In Garch, you could see the persistence in the volatility. So the big spikes are followed by big spikes, okay? So that's the difference. It's not, it's the beta and the beta term with on the conditional variance is basically allowing the volatility to persist for longer periods of time. Okay, in our case, by a lag, but you could see the difference, okay, between an Arch one and a Garch one. So let's formalize what's the difference. So Garch improves upon Arch by adding a memory component beta. You can see sharp increases in volatility in Arch, but it quickly returns to baseline. Garch, however, shows the phenomenon of volatility clustering where volatility persists. So it's important to point out that Garch 1.1 shares similarities with ARIMA, right? It has stationary properties. So in order to find the long-run average of the variance risk, we use the expected value operator. Now we've got this original equation. We just put the expected value on each of these terms. And it'll end up looking something like this. Now the expected value of the random variable, since alpha is a fixed coefficient, we could pull that out from the law of iterated expectations. The average squared shock is the same as the average variance, right? So we saw earlier that we took the expected value of the error term, that's similar to looking at the variance, okay? Now the persistence, we could do the same thing, right? In this case, we pull out the beta term. And in a stationary state, the average variance yesterday is the same as the average variance today. Now that makes sense as well, because we saw that the variance should be constant. It's not changing. So we take an average of a constant, something that's constant or stationary. It doesn't matter. There's no difference between the average variances from today or yesterday. And we could look at this equation, that idea from this perspective. So we see the sigma bar squared that's been used, okay? And that's what the expected value operator did, okay? We're taking the average variance. If we do a little manipulation, we could get to this term here. Omega divided by 1 minus alpha plus beta. So let's look at an example. Garch uses maximum likelihood estimation. It's used to get the parameter estimates. And let's give some sample statistical output you would find when you use Python or whatever, Python R or whatever statistical package. So let's say you get an omega of 0.02, alpha of 0.1, and beta of 0.85. Step one, what would we do? We would check for stationarity. Alpha plus beta is equal to 0.95, which is less than 1, implying a covariance stationary series. Now you could see that if alpha plus beta would be greater than 1, it would be scaled, the variance would be scaled, right, to increase continuously. So it would not be stationary in the sense that it would revert back to some baseline level. Step two, what would we check for? We would calculate the long run variance. And we saw that earlier with the bar sigma squared, which is just the average variance, right? The long run average variance. So 0.02 divided by 1 minus 0.95 is equal to 0.4. The takeaway, even if the market crash spikes the variance up to 2 or 3, that would be heteroskedastic, you know that mathematically the gravity of the model will eventually pull the risk back down to 0.4. Stationary equilibrium. In this graph, the long run variance appears to be a little bit less than 1, different from our previous example. But you can see when it spikes, it gets pulled down to this long run level. Okay. So this is demonstrating the idea of stationarity in the long run. Okay. That even though that there's these spikes, if alpha plus beta is less than 1, it will be stationary, meaning it will be banded. Maybe not in the short run, right? From 100 between 200, we see a spike, but in the long run, it should be reverting to some type of band. So the Garch explanation of the shock. The surprise, E.T. Garch assumes that the actual shock, the news of the dice roll, is random and unpredictable. It has no way of knowing a geopolitical event or bad earnings report will happen tomorrow. Okay, so that's the randomness of the model. Okay, we could actually add indicator variables to our model, right, to see if it has a statistically significant effect on variance. Okay, what I mean by an indicator variable is like, okay, will the Federal Reserve news announcement affect it? We could model that, but in this case, let's keep our model simple. So the aftermath, sigma t, once a shock occurs, Garch is excellent at predicting that the market will remain volatile. So that's the subtle distinction. It will not predict the shock, but it's good at predicting the long-term behavior or the short-term behavior of that shock. Okay, it calculates the regime of risk, telling you that because a shock happened today, the probability of another large move tomorrow is much higher than usual. And then there's a cool down. Because of the equilibrium math we discussed, Garch can also predict how long it will take for the market to calm down and return to its long-term average risk level. And that's the stationary component of Garch, right? So what are some practical applications? We could forecast value at risk. This is a primary tool used by banks to meet international regulatory requirements. It calculates the maximum amount of money a firm could lose in a day by looking at how current market shocks amplify potential losses. Volatility clustering for option pricing. Before Garch, traders assumed risk was a constant average. But this model allowed them to price options more accurately by recognizing that big price swings today almost always lead to big price swings tomorrow. And finally, dynamic asset allocation. Large hedge funds use the models to automatically scale their exposure to the stock market, shrinking their positions when the model detects a high-risk regime and expanding them when the market settles into a stable, low-risk state. I do want to add that Garch does have applications outside of finance, but I've restricted my discussion to the field of finance. So that'll be it. Thank you very much, and I'll be seeing you shortly.